You are holding the modern world in the palm of your hand. Not metaphorically. Literally. The smartphone in your pocket contains a chip smaller than your fingernail. That chip has more computing power than the entire NASA mission control room that sent humans to the moon. And nobody saw it coming. Not the governments. Not the corporations. Not even the scientists who invented it. This is the story of the microchip. The most important invention of the 20th century. And possibly, of all human history. To understand why the microchip matters, you first have to understand what the world looked like before it existed. The year is 1955. Computing machines exist. But they are not what you would recognize today, the ENIAC. One of the first general-purpose computers. It weighed 30 tons. It occupied an entire building. It consumed 150 kilowatts of power, enough electricity to light a small neighborhood. And what could it do? Basic arithmetic. Calculations that your phone does in a fraction of a millisecond, the ENIAC needed seconds, sometimes minutes, to complete. The machine was built using vacuum tubes. Glass cylinders, the size of your thumb, that controlled electrical current. The ENIAC had 18,000 of them. And they failed. Constantly. Technicians worked around the clock, replacing burnt-out tubes, like changing light bulbs in a never-ending hallway. On average, the machine broke down every single day. The problem was obvious. Vacuum tubes were fragile. They were large. They generated enormous heat. They consumed enormous power. If computing was ever going to leave the laboratory, if it was ever going to reach ordinary people, something had to change. Something had to get smaller. In 1947, scientists at Bell Laboratories invented the transistor. A solid-state device, made from semiconductor material, that could do what vacuum tubes did, but smaller. And faster. And without burning out every few hours. This was a revolution. Computers shrank. Reliability improved. The transistor won its inventors. William Shockley, John Bardeen, and Walter Brattain, the Nobel Prize in Physics. But even the transistor had a problem. A single transistor is just one component. A computer needs thousands of them. Connected together. With wires. Soldered by hand. As circuits became more complex, the wiring became a nightmare. Engineers called it the tyranny of numbers. You could make each individual component smaller and better. But you still had to connect them all, one wire at a time. By the late 1950s, the entire electronics industry had hit a wall. And then, two men, working completely independently of each other, in two different companies, in two different states, had the same idea. July, 1958. Dallas, Texas. A young engineer named Jack Kilby had just started his job at Texas Instruments. He was new. He had no seniority. And when the company's annual summer vacation arrived, he had not yet earned enough leave to take time off. So while everyone else went home, Jack Kilby stayed in the lab. Alone. With time to think. And a problem that had been bothering him for months. The tyranny of numbers. All those components. All those wires. What if you didn't need the wires at all? What if all the components of a circuit, the transistors, the resistors, the capacitors, could be made from the same piece of material? At the same time, on a single tiny slab of semiconductor, Kilby wrote down his idea. Then he built it. On September 12, 1958, Jack Kilby demonstrated the world's first integrated circuit. A sliver of germanium, half a centimeter long, with 5 components, all connected, without a single soldered wire. The oscilloscope showed a perfect sine wave. The circuit worked. His supervisor looked at the result and said, simply, "That's exactly what I wanted." Jack Kilby had just changed the world. He just didn't know it yet. 3,000 kilometers away, in the hills of California, another engineer was thinking the same thoughts. Robert Noyce, co-founder of Fairchild Semiconductor. Where Kilby was quiet and methodical, Noyce was charismatic and bold. Where Kilby worked in germanium, Noyce worked in silicon. And silicon would turn out to make all the difference. In early 1959, Noyce wrote in his notebook, it would be desirable to make all of the circuit components in a single monolithic slab of semiconductor material. He didn't know Kilby had already done something similar, and Kilby didn't know what Noyce was building. But Noyce's version had something Kilby's didn't. A way to connect the components using metallic pathways, printed directly onto the surface of the silicon, using a process called photolithography. No wires. No soldering. Just light, chemistry, and silicon. This was the blueprint. This was the method that would scale. This was how you go from 5 components on a chip to 5 billion. The two men would spend years in patent disputes. History would eventually credit both. In 2000, Jack Kilby received the Nobel Prize in Physics for the invention of the integrated circuit. Robert Noyce had died a decade earlier, in 1990. Nobel Prizes are not awarded posthumously. But what exactly is a microchip? Let's slow down for a moment. Because what happens inside a chip is extraordinary. It starts with silicon, the second most abundant element in the Earth's crust. Refined to a purity of 99.9999999%. 9 nines. Purer than almost anything else humans manufacture. This ultra-pure silicon is grown into a single crystal, a cylindrical ingot, then sliced into wafers thinner than a human hair. The wafer becomes a canvas. And what gets painted on it is a circuit. Drawn not with a brush, but with light. The process is called photolithography. A light-sensitive chemical is applied to the wafer. A mask, like a stencil, is placed above it. Ultraviolet light shines through the mask. Where the light hits, the chemical changes. Chemical baths wash away the exposed areas. What remains is the pattern of the circuit. This process repeats, layer by layer, dozens of times. Each layer adding more components, more connections, more complexity. The transistors built this way are incomprehensibly small. Modern chips use transistors measured in nanometers. A nanometer is 1/1,000,000th of a meter. The best chips today have transistors smaller than 2 nanometers. For comparison, a human red blood cell is 8,000 nanometers wide. The transistor on a modern chip is to a red blood cell what a red blood cell is to a house. Billions of these transistors. Each one a switch. On or off. 1 or 0. Binary logic. Built up layer by layer, into the language of computation. In 1965, Gordon Moore, co-founder of Intel, made an observation. He noticed that the number of transistors on a chip was doubling, roughly every 2 years. And as the number doubled, the cost per transistor fell. He predicted this trend would continue. The electronics industry treated it as a roadmap. Engineers designed to it. Manufacturers built to it. Investors funded companies based on it. And for 60 years, it held. 1971, Intel's first commercial microprocessor. 2000, 300 transistors. 1972, Intel 486. 1.2 million transistors. 1973, Intel Core 2 Duo. 291 million transistors. 1974, Apple M2 Ultra. 134 billion transistors. 134 billion. In a chip you can cover with your thumb. Moore's law is the reason your phone is more powerful than the computers that designed it. It is the reason software became more powerful than hardware. It is the reason the internet exists as we know it. It is the reason artificial intelligence is happening right now, in this decade, rather than the next century. Let's be specific about what the microchip actually changed. Because it changed everything is easy to say. Harder to feel. In 1969, the Apollo guidance computer that navigated astronauts to the moon had 4,000 integrated circuits, weighed 32 kilograms, and cost millions of dollars to build. Today, the processor in a $5 microcontroller is more powerful. Microchips made medical imaging possible. MRI machines, CT scanners, digital X-rays. The diagnosis that saves your life runs on a chip. They made modern aviation possible. Every aircraft flying right now is controlled by dozens of embedded processors. The air traffic control system coordinating thousands of flights simultaneously runs on chips. They made the internet possible. Not just the devices that connect to it, but the undersea cables, the routing systems, the data centers, the entire nervous system of global communication runs on silicon. They are changing agriculture. Sensors in the soil. Drones monitoring crop health. Automated irrigation systems. Chips are feeding the world more efficiently than any farming technique in history. They are central to fighting climate change. Smart energy grids. Electric vehicle controllers. Solar panel efficiency systems. The green energy transition is a semiconductor transition. The microchip did not just change technology. It changed what it means to be human in the modern world. It changed how we communicate, how we learn, how we heal, how we work, how we see the universe. Jack Kilby. Working alone in an empty lab. On a summer vacation he couldn't take. Robert Noyce. Sketching in a notebook. In a state that didn't even have a name yet for what he was building. 2 men. 1 idea. A piece of silicon, smaller than your fingernail, that would rewire civilization. Today, there are people continuing that work. Designing the next generation of chips. Pushing transistors closer to the physical limits of matter itself. Building the hardware that will run artificial general intelligence. Designing the processors for quantum computers. Engineering the chips that will one day connect the human brain to machines. The chip is not finished. The story is not over. Somewhere right now, a student is sitting in a classroom, learning about semiconductors, about electron behavior, About nanoscale fabrication. That student doesn't know it yet, but they are being handed the most powerful tool in human history. The microchip. 65 years old. Still evolving. Still surprising us. Still changing everything. Every invention has a story. Every profession has a purpose. This is the Profession Archive, where we document both. If this story made you think, follow the channel. Because the next invention is already waiting.